Bismillah, Assalamualaikum warahmatullahi wabarakatuh. This will be chapter 7.1 and we will be dealing with internal forces. We have covered in chapter 6 forces in trusses, forces in frames and forces in machines. In particular for frames and machines, we focus on solving the forces of the support reaction as well as the forces connecting different members, right? But in this chapter, we'll focus on what is going on or the forces inside a particular member, right? If we cut it off, what is the force inside, basically? As usual, the slides will be available in the description box below, so feel free if you need to follow through this lecture side by side with the slides, feel free to download the slide. So without further ado, let's go to the slide. So the objective for this portion 7.1 is for the student to be able to use method of sections for determining the internal forces for 2D cases, right? So we will focus first on two-dimensional problem. So the design of any structural member requires finding the forces acting within the member to make sure the material can resist those loads. So basically what it means is that in a structure, we have combination of many members, and for each member to be able to design it properly so that we will use a proper material so that it will not fail, we have to know what is the internal forces, right? So when we have those information, the internal forces, then in terms of design we can select a proper material. So that is basically one of the key factor behind understanding this chapter. So in the slide, it gives you a diagram. For example, you need to find what is the internal load at point B. So basically, to be able to solve it, we will have to first solve for the support reaction, and then we will cut and use the method of section at point B to determine what is the three load that we have to determine, which is the normal force, the shear force and the moment. The following slide will give more detail onto how we will determine each of those. So the next slide is just to illustrate that to solve the problem, to solve for internal loading, we can solve using the concept of equilibrium of a body. So as usual, it is basically summation of forces equal to 0 and summation of moment equal to 0. So basically, if you have originally a member like this, right, and we need to find what is the internal forces at this point. So we cut off here and then we draw the force, which is the normal, the shear and the moment. This is if we have 2D problem, and we can solve all these using the three equation of equilibrium. And the following slide, you can see that the convention sign for these three components, right? So on the left side, hopefully you can refer to the slide, right? Because when you split the member, so we can either focus on one side or the other side. Obviously, if you focus on this side, you will draw the forces and normal force, shear force and moment here. If you focus on this one, you will draw here, right? So obviously it will be the same but opposite, right? So for example, normal here is in this direction, normal here is in this direction, right? So the convention is, if you draw on the left side, of you to consider the left side of the member when you have cut at that point, the normal is going out. So similarly on the right, the normal is going out, right? So as you can see in the slide, for shear, if you draw on the left side, the V, which is the shear force, is going down, while if you consider on the right side, it will be going up. And for the bending moment, for the left side, it will be counterclockwise, and for the right side, it will be clockwise. So hopefully you can memorize this, because this is the sign convention, so that when we get we have to use this convention, and if you get negative, it means it's basically the opposite side. Opposite direction, right? But memorize this convention. So the following slide is basically a further elaboration. So in a 2D problem or two-dimensional cases, typical internal loads are normal or axial forces, which we use N, acting perpendicular to the section, And then another one is the shear forces. We use V. This is acting along the surface, and the other one is the bending moment M, right? So the slide actually gives you an illustration if you draw on the left side and also on the right side, right? So hopefully, yeah, on the right side and on the left side, right? And the drawing there shown if actually you cut straight away like this. So obviously if you cut straight away like this, the normal will give out, and then the shear depend on, okay, so if you take the left, right? So if this is straight, so the normal will go out, shear will go down because this is the left one, right? And then the moment will go like this, right? But if you cut at a slanting angle, right? So meaning that if the angle is like, how to illustrate, if the angle of the cut is something like this, right? For example, it is at an angle, so the normal will be like this, the shear will be like this, and the moment will be like that, right? So N will always be perpendicular to the surface of the cut, and shear will be along the surface, right? So yeah, the illustration there is for a straight cut like that. Okay, so another point that the slide is actually mentioning is that the load on the left and the right side of the section are equal in magnitude and but opposite in direction, obviously. So when you combine it back together, everything cancel out, right? So for the steps for determining the internal forces, normally the question will identify at which point do we need to calculate the internal forces, right? Because the internal forces at different point throughout the member may not be the same. For example, if you have forces here, etc. So each point will have different or can have different internal forces, right? So the question will give you find the internal forces here, or maybe find it at multiple points. So for each point, you will have to cut at that particular point, right? So for example, the question say find the internal force at this point, then you have to cut at that point. When you have cut at that point, you should be able to imagine that you have two options, either to focus on this part or the other part, right? And when you have to draw the free body diagram, obviously it depends on which side you take, right? So that's the first thing. Make sure you are able to imagine that it is being cut and which side you select to use to solve, because you have to draw the free body diagram of that side only, right? So if necessary, determine any support reaction or joint forces you need by drawing a free body diagram of the entire structure and solve for unknown reaction, right? So if the member, when you cut, for example at this point, regardless of you take on this side or this side, you have to know what are the forces here or the forces here, right? If all of these are still unknown, then you will not be able to solve what is inside here, the internal force here. So all the unknowns should be known first, right? So if you have support reaction here or connection with other member, sometimes you have to solve that one first if necessary, depend on the structure and the question, right? So that's number 2. Number 3, draw a free body diagram of the piece of the structure you decide to analyze. So as mentioned, you have two options when you have cut it, either on one side or the other side. So draw the free body diagram of which side you choose. Remember to show the N, V and M load at the cut surface. So as we mentioned before, when you have cut, for example originally like this, we have cut, so you have to draw the normal, the shear and the moment, right? And apply the equation of equilibrium to solve using summation of forces in x, y as well as summation of moment equal to 0. Then we can solve as usual. So next we have this example where we are given a structure and we need to find the internal forces at a particular point. So of course you have the slide, but I will also try to put the diagram here, which is the structure, and we are given the load, which is 400 Newton there, and then we need to find the internal force at point C, right? So if you are able to imagine that we have to cut at point C, right? And if you cut at point C, you are left with two options, either to take the left side or the right side. If you take the left side, it seems the easier part, the easier choice, right? Which will have portion AC compared to portion CB on the right side. But we will try to do both, and we will see how different it is in terms of calculation. But of course, in this case, if you can see, either way you choose, either on the left side or the right side, you still have to determine the support reaction first, right? Either at point A or point B. So we'll do that first, because if you straightaway cut without knowing what is the support reaction, you will not be able to solve anything, right? So to solve the support reaction, this is what we have covered before, right? So hopefully you still remember this. So if you have a member like this, and then we have the pulley, so cable here and then cable go here, we have the force here, right, which is 400 Newton there, right? And then here at point A is spin, so we have, let's say, AX and AY, and at point B we have the normal reaction here and B. So in terms of the distance, the dimension, so we have 1.2 meter here, right, which is 1 meter plus that 0.2 meter diameter of that pulley, and then the length here is 5 meter in total, right? So that are the important dimensions. So if we solve for this, let's use that side. Is it okay? Okay, it's to solve using summation of moment about point A equal to 0. If you take counterclockwise, it's positive. So you'll have NB times the distance of 5. That is counterclockwise, and you have 400 clockwise, so minus 400, the distance of 1.2 equal to 0, right? So if you solve for this one, NB, you will get 96 Newton. So if you have solved that, then you have, for example, summation of Fx equal to 0, taking right as positive. So you have AX plus 400 equal to 0. So AX is actually negative 400 Newton, which means it's actually to the left, right? And if you do summation of Fy equal to 0, going up as positive, so you have NB, okay, sorry, AY, and then have plus 96 equal to 0. So AY, oops, is actually negative 96 Newton, which is going down. Right? So that is the support reaction. Now, so if you actually already decide that you want to solve on the left side, then maybe this is the only two that you need, because you will not have this in your free body diagram. If you only want to use the right side to solve, you only need this one, because this one will not be in the free body diagram, right, when you have cut into two. Okay, so going back to the structure, let's solve for the left side first, right? So if we take the left side, so meaning that you have portion AC, basically like that. So A, we already have 400 Newton to the left, and then AY you have downwards 96 Newton. Can you see? Hopefully you can see my writing. Hopefully it's not too small and not too dark. Okay, and then until point C, it's actually 1.5 meter, right? So 1.5 meter, 1.5 meter this length, and this is on the left side, so you have something like this, right? V sorry, this is point C, right? So VC and C and MC. This will be the free body diagram, and you can solve this one, right? So summation of Fx equal to 0, taking to the right as positive, so you have NC minus 400 equal to 0, and C equal to 400 Newton. Then you have summation of Fy equal to 0, taking upwards as positive, so you'll have minus 96 minus Vc equal to 0. So Vc equal to minus 96 Newton, so actually the opposite direction. And if you use summation of moment about C, this is point C, right? About C equal to 0, if you take counterclockwise as positive, so you have MC, this one, right? So plus 96 times the distance of 1.5 equal to 0, so MC equal to, it will be negative 144 Newton meter, meaning it's the opposite way, it's clockwise, right? So that is if you solve for this part. It's straightforward, right? I think if you have already established the free body diagram, the rest is straightforward, because there's not too much forces you have to consider anyway. So what if we consider the right side? So if you have the right side, so I have to invert this portion here, but hopefully you can still, this is basically the thing, right? So it will be something like this, and then we have the pulley, we have 400 Newton here, and then NB is already determined as 96 Newton. So the length will be 2 plus 1.5, which is 3.5, right? This one is 3.5 meter. The height is still the same, which is 1.2 meter. So it is on the right, so you have N this way, V that way, and M this way, right? So VC, MC, and C. Okay, so again point C is here at the point that we cut. So to solve, if you do use summation of Fx equal to 0, taken to the right as positive, so you have minus and C plus 400 equal to 0, so NC will equal to 400 Newton. So it's the same. If you do summation of Fy equal to 0, taking upward as positive, so you have Vc plus 96 equal to 0, so Vc equal to minus 96 Newton. So it's the same, negative 96, negative 96. Obviously the opposite direction will be downwards for this case, or upwards for this case, right? Based on the convention. And if you use summation of moment equal to 0, moment about point C equal to 0, if you consider, let me use clockwise as positive to match this one. So I take clockwise as positive, so I have MC, then we have this 400 still positive clockwise, so positive 400 times 1.2, and then this one counterclockwise, so negative 96 times 3.5 equal to 0. You can try, and the answer should be minus 144 Newton meter, which is the opposite, right? So the answer will be the same for all cases, right? For NC, VC, and MC. So we have shown here that obviously either way you want to solve, the answer will be the same, because that's the answer, right? So this is just options for calculation. For this case, this will be a bit shorter, this will be a bit longer, just a bit, because you have two forces in this calculation, but both are similarly simple and straightforward for this case. Right, so that's basically the end of this chapter. For the slide, it is rather straightforward how to calculate for internal forces in 2D. We have other examples that I will cover in the tutorial, inshallah. So it will be a separate video for the tutorial. We will cover several other questions, which is perhaps not as easy as this one. So if you need for those, please take a look, have a watch at that tutorial video. Until then, thank you very much. Hopefully you have learned something, and if there's anything that you wish for further clarification or you want to point out, feel free to comment on the section and the comment section. Until then, thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and see you in the next video.